All right. Okay, so we're just going to review 7.1, 7.2, and 3, the multiple choice questions and the FRQ. The FR, I'll have to scroll down later, but multiple choice we have ready, but okay. So half-life of 2 minutes, sample contains 16 grams of the isotope. How much time elapsed until 1 gram remains? So 16, half is 8, 4, then 2, then 1. It's 4 half-lives, right? And 4 times 2 is 8, so 8 is 3. Well, we have the answers. I should probably not scroll that far next time. Okay. When an alpha particle collides with the nucleus of nitrogen-14, the nucleus X can be produced together with a proton. What is X? This one. That's 1, 1, right?
Mm-hmm.
So what would that be? That would be
17 and 8.
8. 14, because 14 to 4 is 18. We have 1 here, so 17. 17, 8, X, B. Yep, it's B. Good. The binding energy per nucleon. The per nucleon throws a lot of people off, so just be careful when you're seeing per nucleon and make sure to multiply by the number of nucleons. So if it's per nucleon is 6 and there's 11 nucleons, then total is 66. Right?
Yeah.
Okay. So yep, C. Which of the following is true in respect of both the Coulomb's interaction and the strong interaction between nucleons? That is
C.
C. Yep. Because I would think so too, because Coulomb interaction is just between charged particles, and then strong happens between all nucleons. So yep. A radioactive sample has activity A naught at T equals 0. What will be the activity after 2 half-lives? So after 1 half-life, it's A naught over 2. And after the second half-life, it's A naught over 4, right?
So B.
B. And then it doesn't depend on pressure or temperature, right? Because it's random and
Yeah.
spontaneous. Okay. Element X decays through a series of alpha and beta minus emissions. Which series of emissions results in isotopic X? Huh? Oh.
Okay.
Yeah, I was like, how do you do this? So X becomes, so X has some.
I think it's A, just looking at it, but we can see.
That probably makes sense because that's 2, 4, and then that would be, I would think so, but let's check. So if you have 1 alpha first, that's 2, 4. This will become Z minus 2, then this will become A minus 4, right? So now this is no longer X, this is now Y. Because this is a new element, right? Because it's Z minus 2. Now, if we start with Y, Z minus 2, A minus 4, if we do another alpha particle, another alpha decay, there's no way that's going to happen, right? That'll just make it worse. So we need to get back. So we need to do a beta decay. So beta decay with antineutrino, we'll have, that's 1 minus 0 here, and Z, or maybe like a P, some new element P. I don't know. It's very hard to come up with letters. Let's just go with Z. That'll be Z minus 1. And that'll still be A minus 4. And then the Z element, which is Z minus 1 and A minus 4, will have to undergo beta decay again. It goes beta minus decay again. That'll be X now, because we have Z minus 1 and we have a minus 1 here. So that has to be Z, which is the same proton number we started with. A minus 4, right? Yeah. So that's an isotope because it's A minus 4, but then so 4 less neutrons. What is A? Okay, good. Yep. Okay, this is what I need practice with. Which diagram shows beta plus decay? So beta plus is proton to neutron, right?
Yes.
Proton to neutron, we have up, up, down becoming up, down, down.
Mhm.
So an up becomes a down.
Yep.
So it can't be D, right?
No.
Up becomes down.
And it's beta plus, so you can automatically eliminate C as
C goes
well.
away too.
Because of the W minus, it has to be a
Yep.
W plus.
And then positron has to go in this direction, right? Positron can't go in that direction. So I think the answer is A then.
Yeah. Also, the B has a positron and an antineutrino.
It's A.
So
Yeah, that
yeah.
Okay, good. Okay. 400 becquerel activity and then half-life of 8 days. So after 32 days, the activity is what? 4 half-lives.
Yeah.
400.
D.
25. B. Yeah, because if you just divide 400 by 2, 4 times. Quarks separate from each other within a hadron. Okay, so this is a hadron is any it has 3 quarks, right? No.
Yeah. Well, it can be 3 or 2.
3 or 2, it doesn't matter. What was okay? It's baryon. Baryon has 3. So a hadron is just it interacts with the strong force, and hadron just means it's made up of quarks, right? Or antiquarks. And then baryon means it's 3, and then what's the other one?
Meson.
Meson has 2. As quarks separate from each other within a hadron, the interaction between them becomes larger. What's the nature of this interaction?
I'm guessing C, but I don't know.
I would think so too, because the electrostatic, if this distance separates, the interaction becomes smaller, right?
Yeah.
So,
well, why does it become strong nuclear has a very short range, right?
short. But in that short range, it wants to stick together more, I believe.
Oh, yeah.
I think so.
Probably.
Yeah, I might be wrong, but that's what I would think. So C, strong nuclear. Yeah, it is strong. So yeah, I mean, at that level, the only 2 forces that are interacting are electrostatic and strong nuclear. And gravitational is insignificant at that point, obviously. Weak nuclear is not there. Electrostatic would not work because if its distance is increasing, then the interaction.
Also, I guess just based on the definition of a hadron, like it has strong nuclear force in its definition, right?
Yeah. Okay. 3 of the fundamental forces are that, and then what forces are experienced by an electron? Now, obviously not strong nuclear because it's not a nucleon. Then the other 2?
I think it's 2 and 3, right?
So C. Yeah, I think so too. Yep. Okay, which is following list fundamental forces in increasing order of strength? This is on our previous test.
Yeah.
Gravity is the weakest, then weak nuclear, then electromagnetic.
Yes.
C?
Mm-hmm.
Okay. We've done this one a billion times, but it's A equals C plus N, right?
Yeah, so C.
Yeah, C, if you just rearrange that equation. Okay. Mass defect is that. What's the binding energy? Oh my. Okay. That's in kilograms.
Yes.
They're playing with us. Okay. We have to pull out our calculator. So it's just MC squared, right?
Mm-hmm.
So mass is 4 times 10 to the negative 30 times C squared. C is 3 times 10 to the 8, right? We square that. I get 3.6 times 10 to the negative 13 joules. That's in joules though, right? So
Yeah.
now we have to get out our formula booklet. Oh wait, where's my small formula? I only have large one. Uh-oh. That's okay, I'll just deal with this for now. I'll do it in my notebook or something. Okay, so comes out to 3.6 negative 13 joules. I'm sure it is. I don't know how to do it. Okay, so the way you do this is you know that the elementary charge is 1.6 times 10 to the negative 19 coulombs. So that means 1 electron volt. So this is the conversion factor. For every 1 joule, you have 1.6 times 10 to the negative 11.
Wait, are you supposed to multiply?
No, you're supposed to divide, because a volt is
there's
a
one
joule per coulomb. So is joule per E essentially. That means electron volt.
1 electron volt has 1.6 times 10 to the negative 19th.
1 electron volt has that many joules.
Easy.
That's correct. Yeah, because joules are smaller than electrons. No, joules are bigger, so electron volts are small. So we need to have 1.6 times 10 to the negative 19 joules for every electron volt. Yeah.
Yeah.
This always throws me off because they don't give a solid conversion. Anyway.
It's hard to visualize like what you have to divide and multiply.
Yeah. So now it's just 3 point. Oh wait, you don't get the calculator.
Oh, you don't?
I should not have. Okay. How do we have done this? So that's 4 times.
Don't?
We don't get a calculator for paper 1, I don't think so.
Well, I guess you just have to see that it's approximately going to be 2.
And then 3 squared is 9. 3 times 10 to the 8. So 10 to the 8 squared is 16. And then you multiply that in joules. So that's right now, that's that up to there, that's in joules. And then that will be for every 1 electron volt, we have 1.6 times 10 to the negative 19. So you get 36 over 1.6 times 10 to the negative 30 plus 16 is negative 14.
Yeah.
Negative 14 plus 19 is 19 minus 14, which is 5.
Mm-hmm.
So whatever that is, what's 36 over 1.6?
20.
Well, let's make that 16. If we make that 16, that's 16 times 10 to the negative 1. That'll add us 1 here. 36 over 16 is approximately 2, right? Because 16 times 2 is 32. It's approximately 2 times 10 to the 6 electron volts. So see? Yeah.
Yeah.
So how did you do that so quickly? Did you just do all this in your head or what?
Yeah, kind of.
Yeah, I can't do that at all. Okay. Cool. What? Oh, okay. What energy is equivalent to the mass of 1 proton? So that's just equals mc squared, right? So the mass, we need the mass of the proton times c squared. Okay. The mass of the proton is 1.673 times 10 to the negative 27 kg. But I don't think that's anywhere on. Okay, maybe we might need to do some rewriting. This is a little bit weird. Seven, and then kilograms.
What is the 9.38?
I don't know what 9.38 is. I don't know where that's coming from. Oh, that's 938 mega electron volts per c squared. So maybe they're starting with that. Maybe. Because I don't see 1.6. Because if it was in joules, so it has to be in joules. That's the one way to do that is to do 3.0 times 10 to the 8 squared. That'll get you to joules, because now you're in kilograms and then meters squared over seconds squared. That's one way to do it. The other way is to start using the mass, or using mega electron volts, because the formula booklet will give you that the proton's rest mass is 938 mega electron volts per c squared, and then if you multiply that by c squared, you get it in mega electron volts. But then you need to convert it to joules, right? And what's the conversion for that? It's for every 1.6 times 10 to the negative 19 joule. Nope. We need to put that in the numerator. 1.6 times 10 to the negative 19 joules. We have 1 electron volt. And now electron volts will cancel. And then we'll be left with joules. So we'll have 938 times 1.6 times 10 to the negative 19 times mega. Mega is 10 to the 6, right? So I believe that is the answer. Now, which answer choice matches that?
D.
D. Yes. Because
Wait, I'm a little confused. So did you just put 938 there because you knew that was the value?
Yeah, because I have the booklet here. You need the booklet for this. You need the proton rest mass. Otherwise, you can't calculate the. I just started off with E equals mc squared, and I know that we need to end up in joules, because all the answer choices are in joules. The one option is to do kilograms and then multiply that by 3 times 10 to the 8 squared, but none of the answer choices matches this number 1.673.
Okay.
So that's why I did 938 mega electron squared, multiply that, get rid of, convert back to joules, and D is the only answer. Yep. Okay. Simple model of an electron or of an atom has 5 energy levels, different frequencies. So that's the cascading thing, right? 3, 4, 5. That's 1, 2, 3, 4, 5, 6, 7, 8.
How are you counting them? Can you draw them?
Yes, I can. Let me do it in a different color. Maybe that might be easy. So I always go from top to bottom like this. I go 1, 2, 3, 4, and now from here 5, 6, 7, 8, 9, 10.
Okay.
So that's, and then another way you could do it, I guess, would be, I guess you could do the same thing going the opposite way, where you keep the base the same and then you go up. Same idea. Okay. So C. Yep. Geiger Marsden alpha particles are scattered by gold nuclei. Experimental results prove evidence that.
B.
That's just by definition. All right, can we go to some more that have like 7.3 stuff? Because I feel like we've done enough problems with these.
Yeah, sure.
Okay, good. Feynman diagram shows the particle interaction involving W minus boson. Which particles are interacting?
C.
X and Y? Yeah, C. That one was pretty easy because, I mean, they're both, X and Y are both.
I hate when they put time on the Y.
Yeah, it's just, it messes the whole thing up. I don't know why they do. That's just kind of.
So in this one, they drew W minus with a dotted line, but we should always do it with like a.
Yeah, we should do it with
line,
a strict line. Okay. For which reason were quarks first introduced? to explain the existence of isotopes, that doesn't seem right. Nuclear emission and absorption spectra doesn't seem right either. I don't know whether is it C?
Yeah.
Because quarks are elementary particles, so I would say it's
I think D would probably be leptons, right?
energy and momentum beta. Probably, yeah, like muons and yeah, or anti-neutrinos and stuff like that. So yeah, I would say C. This is good. The reaction proton plus neutron makes proton plus.
Oh, this is one of the fun ones.
Yes. One of the fun conservation. Electric charges conserved.
Yeah. Baryon number. Okay. I think it's lepton number.
Is
because
it?
they're different. They're different species, right? Or like families, you know?
But pion, but pi isn't, is pi a pion isn't a lepton, it's a meson, remember? Pi isn't it's not a lepton. Leptons are electron, muon, and tau. So pi.
Then it's a baryon number.
Baryon number is what I was, yeah. It's strangeness,
Well,
let's see. All of these have strangeness of 0, so it doesn't matter. So yeah, baryon.
Wait, so pion is a meson?
It's a meson, yeah.
Okay.
I don't think like you would need to know that. It's just, I think it's like, or just from what I remember, I saw a problem in which a pion was, it's just said that pion is a meson. So it's like, it helps to know that. Otherwise, I mean, it's not a lepton. There's no leptons. And strangeness is obviously 0. So I would say B makes the most sense. Yeah. Which statement about atomic spectrum is not true? D. This one?
Yeah.
All right, we've done these. Okay. Atomic energy levels we've done this. Nuclear fusion is the joining of 2 small nuclei to create a larger. Transmutation. Okay, transmutation definition is when a particle is bombarded into a nucleus, and the nucleus becomes the nucleus changes into a nucleus of a new element, right?
Yeah.
Is that all you need for the definition? That was our last test, right?
I believe so. Yeah, it was. I think it's B for this one also.
B for this one? Probably 80, 81, 10, 90. Yeah, we need 2, 4 here. So here, yep. Okay. Yeah. Oh wait, what is this? Oh, photon. Yeah, that's fine. We've done this. Oh, this is an interesting question. I wouldn't. Might be worth going over. And compared with beta particles and gamma ray photons, alpha particles have the greatest mass. So because they have the greatest mass, we could have figured that out. But they also have the lowest range in air, right? They interact the most.
And the lowest penetrating power.
Most penetrating, yeah.
And the lowest speed, yeah.
And lowest speed. Okay. What is the mass number of the nuclide if there's this many electrons, protons, just NPN?
Yeah.
Speed. Doesn't seem like there's been too many Feynman diagrams on previous papers. 14, we need 1 for beta plus, positron, and neutrino.
Yeah.
E. Hold on, what is going on?
Oh.
It's stereo. Okay. It's just X absorbs and neutrons give nucleus of Y and Z. Magnitude of binding energy per nucleon of Y over that of X. Total binding energy of Y and Z over total binding energy. Well, these have to be more stable, right? Y and Z have to be more stable than X.
Mhm.
So this should have Y over X should be greater than 1, right? Because this is more stable. Because the binding.
Y and Z over X is definitely greater than 1, but I don't know about Y over X.
How do we know that?
Well, Y and Z over X should have, it should, like, Y and Z, the total binding energy should be even more than just X, right? Or just Y, sorry.
Y and
Like, total binding energy of Y and Z should be even greater than just Y, right? Oh,
Y, yeah, but maybe we can put down some numbers. That might help. So let's just say this is like Z
okay, I see.
N,
Okay.
right? Then this would be, let's say Z minus K, and this would be K, right? And this would be N.
Okay, never mind. I see.
That might not.
I see
That
what's
might
going
not.
on.
Y and Z are smaller, right?
Yeah.
Fission.
So
The total binding energy of Y and Z.
okay, I think it's actually. I think it should be C, but
I think
I'm
it's
not
C
sure.
as well. I think I just feel like the total binding energy of Y and Z should be less than the total binding energy of X. Reason being, Y and Z are the nuclei that make up X, and since they're separated, X has stronger, more binding energy total, right?
Yeah.
So yeah, exactly. X has to have more binding energy total than Y and Z. So Y and Z would be less than 1, and that would be greater than C, I believe.
Mhm.
Watch us be wrong. It's A. Yeah, you are right. So is it just because the combined is just greater? How do you know that?
Wait, but I thought it was like if energy is being released, then the reactant one has to have a greater total binding energy.
That's what I thought too. Or I had to have greater mass, right? No, binding energy. It is binding.
Because binding energy, one definition is the energy released when the nucleons are separated, right?
Yeah.
So wouldn't more energy be released when X is separated compared to Y and Z together?
When X is separated. I think it's because X altogether though, Y and Z.
Oh.
It's like all together. I think Y and Z together will have. Like if you just did.
Yeah, but okay, so one thing is that Y and Z together have one less neutron than X.
Yes.
And I mean, X does
Oh, that's a good point. Yeah. So if Y and Z have one less neutron than X, then it must be the case that. I mean, it doesn't have to be, but I mean, it would be good to. I think it's safe to assume then that X, because it has one more nucleon, it has more binding energy. Oh, wait, but X needs to have less binding energy, right?
Yeah, that's why I was confused.
Oh.
Wait, isn't there an explanation or something?
There's sometimes, there's not always. No, the examiner's report said nothing here. Why is that greater than 1? Maybe, hold on. Let me see if I can, because if we can get a max idea of what the max is, X and Y will be similarly sized, right?
Yeah.
So fission. Was that fission or fusion? Fission, right? Yeah, fission. So if you have X going to here, overall, the change is very small. So if you have 9, yeah, if you have almost 9 here, wait, that was fission. So X goes to this. So if say something like 8 goes to 9 here, you'll have 2 things that are very close to 9 and half the nucleons. So let's say 9 times 4.5. Okay, let's just create some hypothetical scenario. Let's say X started off with 10 protons, and obviously that's not right, but let's just say it started off with 10 protons and 20 here, and then it became Y and Z. Y has 5 maybe, Z has 5, and then we have 10 and 9, right? Because we have to have a neutron extra that's missing.
Yeah.
Okay. So if X is mass number was, let's say here to here. That seems about reasonable, right? 80 to 60. No, really it should be more like here to here. So let's say we're going
to wouldn't it be from like uranium?
Okay, let's say from uranium to here, to 220, because the mass number would change by just half, or about 10. I don't know.
Wait,
anyways, this is confusing. I don't know what I'm doing.
Wouldn't the daughter nuclei have like approximately similar masses?
Why would they have approximately similar masses?
The 2 daughter nuclei. Would they have like radically
they have to add up,
masses?
right? They have to add up to 20. They can't.
I know, but the 2 daughter nuclei, wouldn't the 2 daughters have approximately?
Yeah, so that's why I said about 10 and 9. So that's why I tried to make that approximate.
Yeah, well, the thing is with uranium, if you make it like 220, then the other one would be like, I don't know, like 30 compared to 220.
I see. So I see what you're saying. So if you have 238 on the top here, you'll probably have something like 115 and then 113, no, 123. Is that right?
Yeah.
115 and 123. So if we're going from here, we're going all the way up to here and here. So roughly so we're going from about 7.5, let's say, to 8.5 roughly.
Yeah, I guess that's a pretty big change in.
It's a pretty big change, yeah.
Binding energy per nucleon.
Yes. So total binding energy wise, this is 7.5 times 238, and that's 115 times 8.5, that times 8.5. So let me just see what the difference is. You can calculate this yourself.
Wait, I think I understood it. So binding energy is the energy released when they're formed, right?
Yeah. Binding, yeah, the difference is it's huge. This together is way more than uranium-238, the binding energy. So Y and Z together are going to be way more than X because they're approximately the same.
Okay.
Right?
Okay, yeah.
So it's A, yeah. Hopefully that makes sense. I think I get it. It's just that the small change this large changes in mass number, it's less steep. So
it creates a relatively large change in binding energy per nucleon when you multiply it by the hundreds of nucleons.
Hundreds of nucleons, exactly. Okay. All right.
And so one nucleon difference is not going to I'm guessing it's not going to make a difference. We were thinking that one neutron being missing would make it less than, but I guess.
But really, it's if you go from 238 all the way to 120 and 130 over, like you're doubling that essentially, right? Because there's two
Yeah.
daughter nuclei. So that's overall it's okay. I think multiple choice. That's waves. That's not. That's yeah. That's
No,
waves.
I don't want to forget that.
You're not doing that. Okay. In which region are nuclei most stable? That's C. You know that. Okay. Diagram Mars. Oh, this might be a good one. The majority of the alpha particles after reaching the foil. C and D are not right. C and D.
Yeah,
C is
it's
way
A.
too crazy. Probably
A.
A. Yeah, I think
Yeah.
A.